Good. So.
All right, so I'm going to start here in a second. Just a note about this slide deck in particular. I have a tendency to over-prepare, so I never run out of slides, which is why I'm always more likely to go over than let you finish early, because there's always more cool stuff to talk about. But the flip side of that is, especially for this material, when we start talking about electrons and orbitals and quantum mechanics, I never know where a good place to put a stopping point is, so I just kind of put it all on there. So it's like 40 slides. I don't expect that we're going to get through 40 slides today. And I will just, whatever we don't get through today will be most of the slide deck for next Tuesday. Today's Thursday? Today's Thursday, yes. Yes. So don't, if you see that, don't be overwhelmed by that. And you probably, if you're printing them out, you probably don't need to print out all of the slide deck for next Tuesday, because most of it will be incorporated into what's already there. So a couple random questions that not that random, but science related questions that I said I'd get to. I thought this was phrased in an interesting way. Have scientists already solved the climate crisis in a mathematical sense? Well, solved in terms of, yeah, we run the numbers and we know what we need to do to limit climate change, absolutely. Ideally, that would mean all fossil fuel emissions would stop today. In terms of solving it in a way that's actually politically palatable and is not going to cause a breakdown of the entire economy of the world, no. That's for the economists and the politicians to argue about, and the scientists just say, hey, you guys should do this faster. We really should be cutting back on these. So yes, it's been solved in that we know exactly what the problem is, and we know exactly what needs to happen to mitigate the effects that are already happening. But in terms of being able to actually put that into practice, that's a whole nother ballgame. Which is why science policy advisor is actually a really, really critical role for most politicians these days. Most politicians have a person whose job is to keep current on science trends and what's happening in the world of research, and then advise them on how that should affect their policy. So that's actually a really cool job. You basically just get to have the ear of a politician as somebody who understands science, and your job is to just keep current and kind of guide where they're going to be placing their votes and any legislation that they're writing. So that is actually a full-time job that you can get if you have a science degree. It's a really cool job. It's not one that people tell you, when you're looking for a career to pick, it's not one that usually gets brought up. There's a lot of those in the sciences that are related to the sciences but aren't research. or teaching, which are the two most common places that people wind up. Why does the density of water change based on temperature? So that'll make maybe a little bit more sense when we start getting into how intermolecular forces and how molecules interact with each other. But essentially, it doesn't do so in either an exponential or a linear way, which is weird. It's more complicated than that, because what you're really doing when you change temperatures, you're changing the average kinetic energy of a molecule. But that's not necessarily changing the average distance between molecules in a linear way. So average kinetic energy, so temperature is proportional to kinetic energy. So this sort of alpha symbol is the mathematical way of saying something's proportional, meaning that it's got a direct correlation. So as temperature goes up, kinetic energy goes up. So we can say that temperature is proportional to the kinetic energy of molecules, and we can just use regular physics to say that there's an equation for kinetic energy, 1/2 mass times the velocity squared. So we can actually calculate the average velocity of a water molecule based on temperature. That's all well and good, but it doesn't allow us to calculate how likely water molecules are to break apart from each other and require more space until you get much more sophisticated. You have to look at what is the energy that it takes to break one water molecule apart from another water molecule. And then that energy would have to go into a more complicated equation that looks like the equilibrium constant is equal to E to the negative change in energy over a constant times the temperature. Now changing temperature is definitely going to change how these molecules are able to separate from each other or not, or what proportion of them are able to separate from each other. But it's not in a straight linear sense. And really, this is best at describing a phase change, so something like boiling. We can actually use this to predict when we get to a boiling point based on how tightly bound the molecules are to each other and what the atmospheric pressure is. We can predict the boiling point using this equation, but it doesn't necessarily take into account how the density of liquid water is going to change. It's going to change, but not necessarily in either a linear or an exponential way. It's in a much more complicated way. We'll find that that's a really common trend with chemistry. The physics is really, I won't say really simple. Physics is simple and well understood by physics majors. When you take it to a large enough scale of, say, like 10 to the 23rd molecules interacting, it behaves very differently than when it's only 2 molecules interacting. Let's see. Is human genetic material ever going to be integrated with plant or other animal DNA to produce hybrids? Well, it depends on what you mean, a little bit, because there is I know, did we talk about mRNA vaccines in this class? That was my other class, huh? In general, our bodies are really good at not incorporating genetic material from the things we eat. Otherwise, every time you ate an apple, you would start to express apple genes, which would be a problem, whether it was a GMO apple or not. Right? So our body's really good at avoiding that. But at the same time, there's random things that happen, especially in prokaryotes, where they will randomly encounter other genetic material and then incorporate it into their own. That's one of the main ways that prokaryotes mutate. And that's one of the main ways we're able to genetically modify microbes, is by taking advantage of that. So when it comes to doing it on purpose, then that's a tricky question, right? We do it with selective breeding for pretty much any domesticated species, and to some extent it might not be on purpose, but with humans as well, right? The selection criteria is more or less uniform, so we are evolving as a species a certain way. Doing it directly by modifying our genome is a very big ethical and moral issue. And in theory, I read a news article a few years ago now, I think, about a guy in China who actually did that. He actually was trying to remove a certain gene for a genetic disease from fetuses. Maybe before fetus stage, maybe at the zygote stage of humans. And then implant them into mothers, carry them to term. He claimed he did it. That was a few years ago now, and I haven't heard a whole lot of follow-up, so either they don't know if it worked or not, or it could have just been a hoax and he was making it up. Either way, scientists in general, we have the ability to do that. We're trying not to right now, mostly because we don't know what all the implications might be. We're trying to be responsible as a species for once and not let Pandora out, open Pandora's box until we know what's in there. But it certainly is likely at some point there will be some. The flip side of that argument is if we have the ability to stop diseases like cystic fibrosis by just changing one gene when they're at the single-celled stage, do we have an obligation to prevent suffering? So it's not an easy question to answer from a scientific or a philosophy standpoint.
Well, suffering is inevitable because we have so many people on this planet. If we were to just let those people die, there wouldn't be so many people. Cutting back on the suffering.
Right. So there's
still suffering.
There's arguments from both sides. Right now, where the stalemate is basically like, well, we don't know what else might happen, so we're not going to do it yet, except for this one guy in China who defied every scientist and decided to go ahead and do that. Although I believe he was immediately ostracized and stripped of his position and things like that. But in theory, that's already been done. I don't know if that actually worked that way or not.
I have a question. I think I meant more so like, why aren't we putting chloroplast in animal cells?
Why aren't we putting chloroplast in animal cells? Because it's not quite that simple. You can take things like put a chloroplast in an animal cell, but that doesn't mean that the animal cell will know how to use it or that it'll be functional.
Right, so there needs to be like more development.
Yeah.
Just like, then you have to go sunbathe for like hours every day. It's way less efficient than eating.
Yeah. We could have
Well,
like,
depending.
so there's like everywhere in the building.
Yeah, so using chloroplasts as using chloroplasts as a solar cell, essentially.
Yeah.
And we're doing that. We're modifying existing plant cells like algae to be more efficient and have more chlorophylls, and then using those as ways to produce biofuels. They're doing a lot of that in Arizona as a way to, because you can make biodiesel from algae, and then biodiesel is just diesel. You can use it to power a diesel engine, just like regular diesel. So you could, in theory, make a carbon neutral diesel fuel by using these modified algae. And they're working on stuff like that. When you get further, instead of just promoting more chloroplasts in something that would already have them, it gets really hard because there's a lot of supporting systems that go along with it. That's really hard. So with single-celled organisms, we can do that. That's actually how insulin is produced. Insulin for diabetics is produced using genetically modified yeast. Yeast is a eukaryote, but we've actually modified it to produce insulin that serves no purpose for the yeast. Yeast doesn't have any need for insulin. Insulin's a protein that works as a signal molecule in multicellular organisms. Yeast is not multicellular, therefore yeast should have no need for it. We introduced that gene, and now we have yeast that produces insulin that we can then just kill the yeast cells and purify it, and we have human insulin produced by yeast. So we do a lot of stuff like that, but the more complex the organism and the more complex the genes you're trying to move, the harder it is and the more luck is required.
It's like working on a Toyota versus a BMW.
Yeah, you're working with something where when it's a single-celled organism, we know what everything does basically in a single-celled organism. So tweaking it's not that hard. When you get into something that's a lot trickier, that has multiple parts and differentiated tissues, it's a lot harder. I always get this next question. I like this question though, because the answer is, like most things in science, is yes and no. There's absolutely no evidence to suggest that the stars themselves have any impact on your personality type. However,
Except for the placebo effect.
Except for the placebo effect. I'm such a Scorpio that way. Except for the placebo effect, but no, also the fact that being born in a certain time of year can, I won't say undoubtedly, but it could easily have an impact on your personality. When you just think about kids that are born in January versus kids that are born in July, kids that are born in July in Tahoe are learning to walk outside. Kids that are born in January in Tahoe are learning to walk indoors because it's snowy outside. So just the fact that you're learning to walk in a different environment can change how your personality forms.
Huh.
And being say 18 months, when February hits, and February in I think it's Cherokee is known as the hungry time, the hungry season. I don't remember exactly how it translates. It's basically every culture in the world, February is when you run out of your stockpile before spring hits. So every culture in the world, other than the southern hemisphere where it's backwards, kids that are turning 18 to around February are going to have different experiences and first memories when it comes to, is it a harvest time where there's food so that we don't starve to death? You could easily see how that might have an impact on somebody's personality, right? You could easily see how that might have an impact on somebody's personality, right? So it doesn't have anything to do with the stars, but at the same time, where you were born and at what time of the year, it definitely affects your personality in other ways. Yeah, Rab?
I don't know, I might be wrong on this, but aren't we just like star material? Are we like, if you go back far enough, like in our...
That is a perfect question to lead into this next one. So, initially, everything in the universe, as far back as we can measure, everything in the universe was either hydrogen or helium. Mostly hydrogen. Hydrogen is still the most abundant element in the universe. However, when you get enough hydrogen in a small enough space, you get a fusion reaction that happens, where you end up with hydrogen nuclei fusing with other hydrogen nuclei to make larger atoms, larger elements. So essentially everything in our solar system that is larger than helium is the result of a supernova of a previous generation of a star. So prior to our star's formation, our solar system's formation, there must have been another star that existed where all this hydrogen and helium came together, fused together to make larger elements. And then at the end of that star's life cycle, it explodes and spreads all those elements out until gravity brings them back together again, and they tend to accumulate in certain ways. Our solar system reaccumulated in a way that reformed another star, but then you have different planets that were formed from other material. So the most abundant are silicon and oxygen, but other planets, it's hydrogen, like Jupiter, or Neptune is mostly water, Mars is mostly iron, and that's all a result of the way that that supernova sort of recollapsed on itself. So that's where that big expression, we're all stardust, comes from, because everything that's not hydrogen in your body at one point was a part of a star, which is kind of cool.
So the zodiac, it goes back more to the zodiac. It's like, yeah, it does affect us. Let's see about that.
There's your evidence.
There's your evidence. And to go to this next question about synthetic elements, there are synthetic elements that we can make in a lab using a particle accelerator that don't occur in nature, or occurred in nature in that supernova, but died out, basically radioactively decayed, or we as a species knew to look for it. So most of the radioactive elements that we see in nature have exceptionally long half-life. They last. Half-life of uranium is uranium-235 is about, or uranium-235 is about, we're looking to make more that actually require more energy per gram than a supernova. So we're making them in very, very small amounts, clearly. But in theory, those are elements that never have existed naturally in the history of the universe, as far as we're aware. So, and in theory, there's another row of the periodic table, starts with 119 right here, that we're trying to make some of these elements because they actually are, the theoretical physics predicts they should be stable enough to exist for an extended period of time. and they should have some really, really interesting properties when it comes to conductivity and density.
What kind of properties are you talking about?
Really high density, really high conductivity. They might be useful for making superconductors. They might be useful for making other exotic, they call those exotic materials.
Yeah.
But we haven't been able to make them yet. But in that 121 to 125 range, there should be some useful elements that will actually stick around long enough for us to characterize and maybe even use. Although they will still be exceptionally expensive because it takes more energy than a supernova to make them.
So would you say we're at a lack of energy now prior to other civilizations that have existed just because of all those radioactive half-lives?
So the total amount of energy on Earth, I would
Are we as a civilization
Oh.
at a lack of energy just because of those radioactive half-lives? Like prior civilizations could have harnessed that energy better than we
I mean, in
are
theory,
using
they-
the energy that we have.
they could have, but they would have to be around first. They would have to know to look for it.
Right.
Yes, there's less radioactive material immediately available by mining things. There are uranium mines where they literally, mine uranium ore and process it for power plants.
Mhm.
There's not a significant amount less of the uranium than there was when humans as a species first started to exist. Because humans as a species have only existed for maybe 250,000 years.
As far as what we know.
As far that's pushing it.
At
We're
least
pretty
modern
sure.
humans.
Yeah, modern humans. Don't go back further than that. So it'd be within sig figs. There's the same amount. That's not enough time for a significant amount of uranium to decay.
Okay.
Jordan,
Then there's also like the Kardashev scale.
I have not heard of that.
Basically, we only have one sample size of civilizations. That's us. The Kardashev scale is the theoretical thing you'd use to classify civilizations based on energy use.
Yes.
So
So I have heard of this then. So a Dyson space, a fully evolved civilization would be capable of harnessing all of the energy of the star that they
that's a
orbit.
Type 2 civilization. Type 1 is able to harness the energy of their planet. Type 2 is the star. Type 3, I think, is either galaxies or multiple star systems.
Right. So it's a hypothetical situation,
and then
but
it
there
goes
is
on
a
to-
right.
Clusters, superclusters, and then Type Omega, which is the weirdest one, harnessing the energy of the universe.
Which arguably we're doing that just not very efficiently.
Yeah.
All right. Let's get back on topic though.
Yep.
Not that I don't love a good science fiction digression.
You got plenty of time for it.
So this, if you had any chemistry before, this should be, I won't say review, it should be somewhat familiar to you. If you haven't had chemistry before, that's okay. This is where we ended the other day. We said that an element is defined by how many protons it has. So all those synthetic elements we were just talking about, we're making them by firing other elements at high energy at each other just to see if the nuclei stick together and make something new.
Mostly hydrogen, right?
No, we're getting in bigger things. Like for instance, you can take a calcium ion with 20 protons and fire it at a lead ion and get something that would have 20 plus 82 would
Okay.
have 102 protons at that point. So that's why it's not always predictable when we're going to find new elements. A big chunk of it is guess and check. They're like, well, what happens if we use this isotope of calcium and add it to, neodymium? What are we going to get? Does it actually stick together? Because they don't always stick 100% together. Sometimes they stick together, but then fragment a little bit. So a lot of it is like fire stuff together, see what comes out.
Let's see what happens.
And exactly. It's been said that the scientific method could be boiled down to fuck around and find out, but write it down.
You gotta write it down, yeah.
Basically, that's what most of these particle physicists are doing. Let's try this one today. I have time on the CERN Super Collider. Let's go over there and we'll try these 3 things today.
Then you get like the real weird stuff like antimatter.
That's a whole different thing. We'll get there.
Okay.
Hold your horses.
I know it's
We'll get to
so
nuclear
weird.
stuff in the 3rd quarter, and we talk about antimatter actually. We can actually calculate using E equals mc squared. We can calculate the energy of an antimatter reaction. It's a real thing we can do. They did it at Berkeley. Berkeley's good at stuff like that. If we're not changing the number of protons, then usually we're changing the number of ion, or the number of electrons, which means we're changing what the ion is. Ion is defined by the net charge. So an ion is, all we do to figure out the net charge is just remember that an electron is negative, proton is positive. Figure out if you have more electrons than protons, you're going to have a negative charge. If you have more protons than electrons, you get a positive charge. Right? It's just adding things up, and we're always going to do it in multiples of 1. We're not dealing with anything fractional or dealing with coulombs or anything like that. You just count how many protons you have, how many electrons you have, and get the net result.
There are certain ions that like cancel out. You get the exact same number of protons and electrons. Doesn't have
So-
a charge at all.
I'm glad you mentioned that, because that's not defined as an ion. We just call that an atom. An atom is neutral. An ion has a charge,
Whether it's positive or negative.
whether it's positive or negative. In fact, a cation is a positive ion. So if you have more protons than electrons, you have a cation. And if you have a negative ion, it's an anion. There are lots of different ways to remember these two things. Some people like to go with the cats have paws approach for cations. I always think anion stands for a negative ion. That's not actually where it comes from. It comes from the same roots as cathode and anode in batteries, because they were able to make batteries before they knew what electrons were. So it doesn't come from that root, but you can remember it that way. The easiest way I always remember it is T looks like a plus sign. Anion stands for a negative ion. And we'll come back and revisit that as well. But anytime we say something is an atom, we're talking about it being neutral. And then last but not least, an isotope is just anything where we're specifying a specific number of neutrons. So an isotope is defined by the total particles in the nucleus. Basically, rather than just how many neutrons you have, you add up your protons and your neutrons. Those are all the things that have mass to them. So if we said something like calcium, I'll write it out first, calcium 41. That's specifying a specific isotope of calcium. Calcium is number 20 on the periodic table.
So we have 21 neutrons.
So you'd be at 21 neutrons. Right, the protons plus the neutrons have to add up to this number, what we call the mass number of that isotope. Right, so, and everything, even the numbers that are on the periodic table, every atom is a specific isotope. Sometimes isotope gets mixed up and people say, well, it's not an isotope, it's the most common form. Well, the most common form still is an isotope, it's just the most common isotope. So carbon-12 is the most common form of carbon. It's still an isotope though. There's also carbon-13 and carbon-14. Carbon-12 is the most common isotope. But what we get in nature, and what these masses on the periodic table are representing, is actually the average of all of the isotopes. Right, so these are actually for the mixtures of the different isotopes in the ratio that we find them on Earth. So other planets where other isotopes are more or less common might actually have different atomic masses on their periodic table. Their periodic table would look the same, but the masses might be different. Because, for instance, on Mars, there might be less of a specific isotope of iron because it's not as dense, or something like that.
Maybe elective isotopes decaying at a different rate now since 1950?
No.
No? Then why do we use C14 to date like 1950?
So if you're using carbon-14 dating, so they're not decaying at a different rate, there's more radioactive isotopes in the atmosphere. So it's harder to use radioactive dating to date things post World War II, because once they started doing all the weapons testing and nuking Hiroshima and Nagasaki, there's all of a sudden there's way more radiation in the atmosphere than normal. There was radiation in the atmosphere prior to that, but it was predominantly caused by sunlight. Sunlight hitting the upper atmosphere and causing nitrogen to turn into carbon-14. And then that carbon-14 can get incorporated into plant matter because plants take CO2 and turn it into sugar and turn it into cell walls and cellulose and everything else. So everything that eats or photosynthesizes is constantly taking in a certain amount of carbon-14. So what carbon-14 dating does is it says, okay, well, for this period in history, here's what the level of atmospheric CO2 looked like. And we can actually go, and it's decayed by this much since then. Therefore, it must be this old. We don't date how old the object is, we date how old the living thing was. When it stopped breathing or eating is when it stopped taking CO2 into its body, which means that's the point at which carbon-14 started to decay. So since then, it gets more complicated because we can't just use the same background levels of radiation that we used to use to predict that. But at the same time, we actually have records now going back to 1950. So we could actually just directly compare. So, okay, for 1961, this was the level of atmospheric carbon, or of atmospheric carbon-14. The problem is that it's not enough time for the carbon-14 to degrade enough. So we can't date things that are too new using carbon-14 dating because it takes about 5,000 years for the carbon-14 to degrade to the point where we could measure. It takes about 100 years for it to degrade enough for us to actually accurately date it. We just don't have enough sig figs, because when you're looking at something that's only changed by 0.01% and your uncertainty on your sig figs is 0.1%, then your uncertainty outweighs the precision of your data. And at that point, it's useless. Uncertainty, it matters.
Finally, example.
All right, so here is our guide to using the periodic table to figure out how many protons, neutrons, and electrons we have. So on the periodic table, this is just a zoomed in version of the simple one that is on the website. We have 4 main components to it. You've got an atomic symbol and your element name, which are usually related, but not always. The mass number, and that's that average mass, here on Earth anyway. And then you've got the atomic number. The atomic number is the most important for us right off the bat, because the atomic number is the number of protons in the nucleus. So because you can't have a part of a proton, this is a counting number. You can't have anything that's in between nitrogen and oxygen, because nitrogen has 7 protons, oxygen has 8. Since you can't have a part of a proton, things are either one or the other. So the atomic number is just a way for us to count easily how many protons there are. And it follows along the periodic table from top to bottom, and your lowest atomic numbers at the top left. Hydrogen, then you read across to helium, then you come back to lithium, 3, 4, 5, 6, 7, 8, 9, 10, and so on. All that's telling us is that's the number of protons for that element. And if you change the number of protons, you change the element. And so if you knew something had, 17 protons, here's our abbreviations that we use. Proton is positively charged, but it's not an element. So we use a lowercase p with a plus to the top right to say it's got a positive 1 charge. So this is a proton. Is p superscript plus. If we want to know, if we have an element that has 17 protons, we don't want to know what it is. Yeah, we just come to our periodic table and we say 17, that's chlorine. Boom, we know what it is. So in other words, the atomic symbol and the element name and the atomic number are all mean the same thing. Right? It's all 1-to-1. There's never any time where the atomic number 18 is not argon. That's a contradiction in terms. Right? So it's the element names and symbols are actually a little bit redundant. You could just do it with just the atomic numbers. But
You have multiple languages.
we have multiple languages. We like having names for the elements for
Well, we're
whatever
speaking in
reason.
numbers and we're speaking in English, so that's why we have the name and
Yeah.
the number for it.
You could say atomic number 18 instead of saying argon.
Yeah.
But that's just not how science developed originally. So if we have an argon atom with a mass number of about 40, how many protons, neutrons, and electrons does it have?
Yeah, 18 protons,
We just said 18 protons, right? By definition.
18 neutrons. Or, no, 18 electrons, and then you know that you have whatever left over in neutrons.
22 neutrons.
It's going to be 22 neutrons. So let's do this one first. So because it's neutral charge means you have as many electrons as protons. So the fact that it's argon tells us it has 18 protons. The fact that it's neutral tells us it has the same number of electrons. And then the mass number is going to be the sum of protons plus neutrons, because those are the only things that have weight within sig figs. An electron weighs as much as 0.0005.
It's 2,000.
2,000 times smaller. So 1 divided by 2,000 would be the relative mass of an electron, which I might have slipped a decimal place. It's either 0.0005 or 0.0005. Either way, it's lost in the sig figs for the most part. We're mostly just looking at protons and neutrons when it comes to the mass. So if we know that our protons plus neutrons has to add up to about 40, then 18 plus 22 neutrons gives us a mass of 40.
So when we're doing that, do we always do numbered sig figs? Because our protons still need to react around the mass number to sig figs or no?
No, when we're talking about this, we're actually counting discrete objects. So these are all exact numbers. Despite the fact that the mass number has decimals, remember that's the average of all the masses and how frequently you find them. Right, so it's a little bit like if you had a roulette wheel where you could get anything between, I don't know, how high does the roulette wheel go? You get anything from 0 to 45, is that? Anybody play? Anybody gamble? No locals ever go to the casinos, right? Unless you're working. Yeah, but taking the average of all those possibilities wouldn't necessarily be an exact number. When you look at the results of an individual ball, it has to be 23 or 24. It can't be in between. But when you take the average of all the possibilities, you could have a decimal. And so that's what this is. This is our average of all the possibilities. If you picked 100 argon atoms and averaged out their weight, this is what you would get. But every individual argon can only have a whole number of protons, neutrons, and electrons.
And the question is in regards to one argon atom.
And the question is in regards to one argon atom. Tiana?
So do the protons and neutrons weigh the same?
More or less.
Mass numbers units are about one of
Yes.
that unit is diluted.
Exactly. So we basically treat them as though they weigh the same, because they do within sig figs. They weigh about 1 atomic mass unit, and which also translates to be 1 gram per mole, and we'll talk about what that means in a minute. But when we're counting these objects, it's a counting number. So these are exact numbers, no need to worry about sig figs, only whole numbers. All right, so let's talk, before we start practicing these, and then we'll take a break and come back and practice more. When we're writing these atomic symbols, so I made a big deal of the fact that that's a lowercase p, a lowercase e, a lowercase n. So just like with units, capitalization matters with elements. elements are always written so that the first letter of their symbol is a capital, and the second letter, if there is one, is lowercase. So if we wanted to, we would never, even if you normally write in all caps, you can't write argon like that.
You got Arizona.
Or you got Arizona, right?
No, it's easy.
Even that is not preferable. Arkansas, yes. So for some of you, you might actually have to change your handwriting slightly when you're writing atomic symbols to make it explicitly clear what the element is. If you normally, it's probably more common, people that write all in lowercase. Like, I don't want to see that for argon either. Right? I'm not discriminating one way or the other against capital writers or lowercase writers. Nobody's allowed to do it. Right? And even, I used to have really sloppy handwriting, or even worse, I should say. But I actually, when I first took chemistry, my teacher forced us to write our L's as cursive L's to distinguish between a capital I. So C, that's not chlorine. That could be carbon with an iodine. It's not clear what that is. So at the very least, make sure you put a little tail. But the way I usually do it is I just write it like that. And now it's just second nature to me, and anytime I write chlorine, it's C cursive L. Right, to make it explicitly clear, this is chlorine, not carbon and iodine. All right, so, and when we're writing these, we have several different modifiers. So charge is one of the modifiers that we put on these to indicate how many electrons we have. And charge always goes up and to the right. The number of objects, or the number of atoms that you have, goes right there. So chlorine gas is, when its pure elemental form, is actually Cl2. There's two chlorines bound together. So down and to the right is how many you have. Up and to the right is the charge. And if nothing is written there, you can assume it's 1. Occasionally, when we're being very, very specific, we will write things to the left to indicate specific isotopes.
We write this argon example.
So this argon example, if it's neutral, it doesn't have a charge, so we wouldn't write a charge here. Or if you do, make sure that it's clear that it's a 0. There's only one of them, so we don't write a number to the bottom right. Number up and to the left is the mass number. So if we want to say specifically this is an argon 40 atom, we would write 40 right there. And then down into the left, this is the atomic number. So to be most complete, we could write it like that. That's redundant if you're already argon though, right? Because argon is always 18. It's never not 18. So there's really not a reason to do that. So your mass number goes up and to the left. Your charge goes up and to the right. And number of atoms is down and to the right.
Is it okay to write 40 even though it's not like exact?
Yes, because if we're talking about a specific atom, it is exact. The mass of that, because of the strong force and the weak force and the way nuclear forces work, the mass is not actually the same as the mass of 18 protons plus the mass of 22 neutrons. There's additional energy that goes into holding these things together, which is actually what led to E equals mc squared. Part of that came from the fact that the mass of 18 protons and the mass of 22 neutrons is more than 40. But the mass of an argon 40 atom is less than 40. Barely, but by enough it's measurable. That difference in mass is the energy that goes into holding the nucleus together. It's called nuclear binding energy. And when you split the atom, that's the energy that's released. More hinting at radioactivity to come. All right, so when we're filling out these tables, you don't need all of the information. Because if the symbol is written properly, you can get all of the information about protons, neutrons, and electrons. So for instance, if we have this right here, C, capital C, is carbon. And I'm not going to make you memorize where everything is on the periodic table, or what its atomic number is, or anything like that. But what I am going to make you memorize is going from symbols to names and names to symbols. So you don't have to know right off the bat where silver is on the periodic table, but you've got to know that it's Ag for some reason. Because otherwise we can't hold a conversation or do these problems if you're mixing up fluorobium and fluorine because you mixed up their formulas or their symbols. You're not going to be able to solve the problems properly. Right? So this is the one time I will say, trust me. This is one of two times I will say, trust me, just memorize this. And we will have a closed book quiz a week from today. On the first, I'll go to the first 6 rows of the periodic table.
Nice.
You know, we'll do the whole thing.
Great.
I'm not going to pull too strongly from down here,
Bastard.
but at the very least, you should be able to get close. So
Closed book test.
Well,
On just this?
Come on, go down like 4 rows.
we're at least going to row 6, including the first row of the F block, because this is part of row 6, actually. So we'll go row 6. I'll leave off all the synthetics down here.
Thanks.
So you don't. That's a gift. Trust me.
So generous.
You are one hell of a guy.
Well, the reason I hesitate there is because there are things that are historically relevant that we will be dealing with, like francium and radium and uranium, that are in that 7th row. But we're not going to be dealing with them as much as everything else. So we'll stick to row 6, including the first row of the F block. A week from today. It's going to be, I usually do 20 where I give you the symbol and you write the name. No, you could do it the other way. 20 where I give you the name, you write the symbol, and 10 where it goes the other way. Chosen more or less at random.
So I can memorize the protons, the neutrons, and the electrons?
No, you don't have to memorize any of that. Just the name and symbol.
Oh, okay.
Name and symbol.
Name and symbol. And when you, in doing that, you're going to wind up memorizing at least more or less where they are. I don't have this all memorized. I know generally where chromium is. It's right there. Yeah.
Wow.
That was actually closer than I was anticipating. It's somewhere in the middle. Right? And then you can always find it. But you've got to know the name so that if I say chromium, you know to go looking for CR. Right? Because
Not CH.
otherwise, not CH, exactly. All right. So with that out of the way, let's fill in a couple rows here. C is carbon. Most of them are related, right? And actually a good way to study them for the ones that aren't related is to figure out why they're not related. Go look them up on Wikipedia. Like tungsten is W. Well, that's because it was discovered in Germany roughly the same time it was discovered in England. The guy in England named it tungsten. The guy in Germany named it wolf, which is a word in German. So as a concession to the two of them, they keep the English name and the German symbol. A lot of the ones that were known in ancient times, like gold, silver, copper, lead, tin, those actually go back to their Latin roots. So gold in Latin is aurum, so it's AU. Silver is argentum, so it's AG. Copper was cuprum, so it's CU. Mercury is Hg, because in Latin it stood for hydroargentum, because it's a liquid at room temperature. It's a liquid metal. So they named it liquid silver, hydroargentum. So that's why it's Hg. So if you learn some of those, that can be helpful for remembering the exceptions. At least I always found it to be helpful. And most of them, when in doubt, go with the first 2 letters of the name, right? That usually will be right. unless there's only one letter in the symbol, right? Fluorine, I see this one every time. This is why I make a big deal of it. Fluorine is not FL. FL is fluorobium. It's a synthetic element. Fluorine is just F. So, and you don't have to get everything perfect, although you could if you're good at memorizing and you spent some time with some flashcards. Most of them you're going to be able, you could probably take the quiz cold and get a C on it today.
Send it.
Let's
Seize
go.
the
I'm ready to
degrees.
test my memory.
Hey, Sean, I gotta ask, just
Yes,
because, will we also be graded on spelling?
that's a good question.
No.
So, yes and no.
Alright.
If a reasonable person could look at what you wrote and get to the right name, I'll allow it.
A reasonable.
So a
A
reasonable,
reasonable person.
I'll tell you what's reasonable is mixing up the U and the O in fluorine and writing fluorine instead. That's
Oh, I
reasonable.
honestly thought that was the exact same.
So that's okay. What's not okay is leaving out whole syllables.
Like lithium?
Instead of if you have ruthenium instead of ruthenium. Like, then we're getting some gray area, right? Would a reasonable person be able to look at that and know that
Is
you
it
meant
cool if I write
ruthenium?
it in Old English?
Old English, if you want, if you have the
Now
time.
I'm just messing with you. Like, if you guys ever tried to read
I
Old
grade
English?
everybody gets.
We don't have time for jokes here.
Yeah, but the other really common one is stuff like molybdenum. Molybdenum is spelled like molybdenum. If you remember it, molybdenum, and you write it as denim like the fabric instead of ending in a UM, I'm going to give you full credit. But if you left out a whole syllable in the middle and wrote molum, that's not reasonable, right? So it's a little bit of a sliding scale. I'm going to,
Okay.
We'll
see what you write down.
Right, exactly. Get close as you can, but don't worry as much about memorizing the spelling.
Do you have a song by any chance?
There are lots of songs. I never learned it that way, but YouTube is full of periodic table songs as ways to remember. Although usually they're helping you remember the order of the elements, not necessarily what their symbols are. But you can probably find some stuff like that too.
Orbit.
All right, so let's fill this out. Now that we've, this is the only time I'm going to take your periodic table away, is for this quiz next Thursday. After that, it's yours and it's your safety blanket, and I will never take it away from you again.
Goodness.
Carbon.
Carbon.
Yay.
Yeah.
Carbon.
6 protons.
Carbon 13 technically, because we're talking about a specific isotope. I know I didn't write it here. This should be chlorine 35 and calcium something. We'll figure that out in a second.
6 protons. 7
Calcium or carbon's always 6 protons. They have to add up to give us 13.
7.
So 7 neutrons. And it's neutral, so the number of electrons matches the number of protons.
Okay.
So for the next one, 18 electrons.
And technically, this is chlorine 35, because we can tell from the mass number here what the isotope is. So if it's chlorine 35,
So it's 17.
17 protons,
18 electrons.
it's got a negative charge, so it has 1 extra electron. There's 18 electrons. Our neutrons just have to add up to 35 with the protons, right?
18.
So another 18.
That's
Lithium.
yeah,
Lithium.
Lithium.
And what's the isotope? What's the mass number?
7.
7. Lithium 7. Symbol for that is going to be Li with a 7 to the, up and to the left. Is there a charge to it?
No.
No.
No charge.
And you put
It's
3
free.
with the 7, right?
No charge.
Nice.
I've heard most chemistry dad jokes. Somehow that one has not come up. No, actually that one has come up. Neutron walks into a bar and says, "I'll have a beer." The bartender says, "Oh, here you go. It's free. It's on the house." It's what? For you, no charge. But
So then when we're writing lithium like that, in this diagram, would we put the 3 underneath that 7, or because that's lithium.
It's implied for the sake of showing that it's there, that that's really the atomic number, you can put it. That's really the atomic number, you can put it. I will never mark you down for putting that. It is a little redundant. The fact that it's lithium already tells us it has 3 protons. Calcium,
20 protons.
20.
Calcium 42.
So it's number 20 on the periodic table, so it's 20 protons. We know the symbol for calcium is Ca, or at least we're learning that. It's going to have a +2 charge because we have 18 electrons and 20 protons. We have two extra protons. And it's calcium, what?
42.
42. You add these together to get the isotope. I don't know why they defined it that way instead of just making the number of neutrons, but they did. So it's calcium 42.
When there's a plus, like a positive or negative sign on the number above the the charge number, I've seen it like after it and before it.
Yes,
Does that matter?
it does not. If it's in the charged position, it doesn't matter whether you write -1 or 1-. Mostly because there are some elements where when you type it, it's easy for the negative sign to look like it's part of the letter. I think bromine is guilty of that a lot. If that's written really small, it's really easy for that minus to look like it's part of the R. So when it's convenient to make it really explicit, sometimes we switch the order on them, but it means the exact same thing. If you can do this, you can do at least 10% of your midterm. 10% of the points on your midterm are this, right here.
Got 10% done.
Right? So get this down so that you don't miss any easy points. We don't want to miss easy points on the midterm. And we'll keep practicing with it. This will be second nature, and it'll show up on the final again. It won't be a full 10%, but it'll be at least 6%. All right, let's take a break. Let's come back at 10 after, and we'll start talking about electrons. Actually, we'll do more atomic mass first.
Sean, you mind if I grab one of these?
Nope, that's what they're there for.
Which one would the ICAP do next Thursday
Thursday. Yeah. So same deal. I'm almost always going to give you a full week to work on things, even if even if I would recommend you do it before then. Like with the labs, this week's lab, if you don't have it turned in, then you're missing out. But for the 1-for-1s, yeah, you have a full week.
Yeah, that lab's due this week's lab is due
Next Tuesday.
yeah, that.
I did this for sophomore year high school time. You have another one every place. It's just like,
got a question for you.
Mhm.
For turning in the lab, free lab, do you like them all together? With the ICAs separate?
So ACA separate, but the labs together, yeah, just staple all that together. I don't have a stapler though.
How about one?
Fantastic. Yep, please.
Does it matter that
If I know that there's 2 pages, anything that I'm missing on the front, I'll go with
Okay,
it.
cool.
No problem.
Put it in there. I think this might be the.
Other side. Look,
Got it.
not that I wouldn't eventually.
No, I haven't gotten that far yet.
That's the density lab. I think you already turned that.
Yeah, all turned in pretty much.
Okay. So I'm still giving you till 10 for break, but if you wanted some more practice with this, there's some more practice. We're not going to go through all these in class, just so we can keep moving along. But I'll fill in the answers here.
Fifteen protons for positive. 16 neutrons. And 13. Well,
-3 charge, right? So 3 extra electrons. That's that part that Benjamin Franklin screwed up. We have extra electrons because the charge went down. Wasn't his fault, but
I screwed it up too.
exactly.
9. Flames, 9.
No,
right?
so it's typo.
Not even that for break, and why you write down the
Gotta keep moving along.
Wouldn't it be 8 neutrons? Since it's 19.
Yeah, sorry, since I not 8, 10.
Okay.
Potassium is one of those ones that has a funny Latin name. Latin name for potassium is potass. No, it's callum. Sorry. Potash is what they called it. Why it's named potassium now. Potash is also known as soda ash or soda lime. And it's potassium hydroxide. It's really, really nasty caustic stuff. But that's where potassium gets its English name, and its Latin name was callum, Kallum.
19 protons, 20 neutrons, and
Plus 1, so 18.
What do they even use soda ash for?
You see it in a lot of things. It's lye is another common. So sometimes lye means sodium hydroxide, sometimes it means potassium hydroxide, or a mixture of the two. It's used to be used in soap making. Gets used a lot anytime you want to just really destroy some proteins. It's really, really nasty stuff. You get something really basic like potassium hydroxide on your skin. You don't feel pain the same way you do with something really acidic because basic substances are a lot less common in nature, so we don't have a real a pain response that's evolved to deal with that. But what does happen is your fingers get slippery. That's actually your skin cells dissolving.
Oh, geez.
So when you're dealing, but it doesn't actually hurt until you get through all the way through most of the layers of your skin.
That's horrifying.
It's what they used in Fight Club, right? When he does kisses his hand and then dumps a bunch of sodium hydroxide on it, and then makes him hold it. Well, he makes himself hold his hand there. But it wouldn't actually start hurting right away.
No
It
spoilers.
started freaking out right away, right? That you wouldn't have actually felt it right away until it started getting down into the tendons, basically.
Used for ceramic glazes.
Ceramic glazes,
Certain
yeah.
ones.
And there are actually some parts of the world that still use the Latin-based names more commonly than the English-based names for things like potassium and sodium. So sodium is Na, which in Latin is natrum or natrium. I think it's natrum. And there are parts of Eastern Europe, especially, I know in Armenia and some of those, not Russia, but Eastern European countries, they still call it natrium instead of sodium. So it's one of the places where there is some translational errors, although they still use the same symbols.
I
So-
was thinking more like all the Romance languages countries, because their languages are descended from Latin.
True, and most of them do not actually do that. In fact, they do other things that are English actually. The English actually put some different spellings, like sulfur is actually with a PH instead of an F. And phosphorus has an extra letter in, I think it's OUS in British, but it's just US in English, in American. There's some other weirdness like that, like they say aluminium instead of aluminum.
Spelled differently too.
What's that?
It's spelled differently too.
Yeah, they spell it aluminium. They put an extra I in it.
And labor color for adding U's and stuff.
Yeah, they add and use all over the place, but you do see that with
Elevator, a
like.
lift.
Pudding doesn't mean
Exactly.
here,
Plum
yeah.
pudding is not a dessert.
yeah.
It's not pudding.
All right. So here's another one that does have a, its Latin name. So this is another common one. It's another irregular. Pay attention to is iron ferrum in Latin. So Fe. So Fe is iron. When we look at the mass units or the mass numbers on the periodic table, we're not talking about one specific isotope or one specific atom anymore. We're talking about the average that we find in nature on Earth. That means that this unit is not always going to be close to a whole number. If it works out that you have almost an equal number of two different isotopes, you could wind up with this number not being anywhere near a whole number. So for instance, chlorine 37 has a percent abundance of about 25%, roughly. No, 50%. And chlorine 35 is very slightly more common. No, I did have it right. That's to add up to get to 35 and a half. So yeah, wind up with, I think it's 3 to 1. I think it's 75%, 25%. Was on my initial guess. So the atomic mass is actually going to be the average of these two. So 35 times 0.75 and 20.25 times 37, without worrying about sig figs, that these numbers or masses are pretty close to the whole numbers. So the atomic mass that we see on the periodic table for chlorine is 35 and a half. When you do the math and add these up, Anthony, you have a calculator out?
Sorry, I was studying the.
Oh, no worries. I wasn't trying to call you out. I was just looked like you might have been doing the math for me. I think this will come out, if I remembered all my numbers properly, this comes out to be about 35 and a half.
Exactly 35 and a half.
Exactly 35 and a half, because I picked the round numbers. So that's why sometimes we have atomic masses that don't match up with a whole number. Each of the individual atoms will have a whole number of protons and neutrons. But the average mass is going to be dependent on not just what the mass of the isotopes are, but also how frequent they are. So things that have a mass that's really close to a whole number generally means they don't have a lot of naturally occurring isotopes. What you're seeing is the most common isotope on the periodic table. But that's not always the case. And these mass numbers, we also don't really want to be talking about individual atoms when we're actually talking about things we want to try and measure, right? Because we can't measure individual atoms particularly well. Turns out we can use electron microscopes to visualize where individual atoms are now directly, but it's still not all that easy. And it's still way easier in our lab, since we don't have an electron microscope, to just deal with large numbers of atoms. And so we have this definition that says, okay, an atomic mass unit is mass for an individual atom. So if we pick an iron atom at random, the average mass that we're going to get is 55.845 AMU. And AMU is this really, really tiny mass, where 1 gram is 6.022 times 10 to the 23rd AMU. Atomic mass units are not that useful for that reason. Nothing can actually measure individual AMU. So what we do instead is we group them in grams per mole. And so a mole is basically just a way to count a specific number of atoms. So a mole is of anything is equal to that many of that object. So the really tired analogy is it's just like a dozen. If you have a dozen of something, that means you have 12 of it, right? You can have a dozen eggs, a dozen cars, a dozen motorcycles, a dozen snowmobiles,
Unless you're a baker.
unless you're a baker, but we'll ignore that. Let's not confuse things further right now. So all it does and is a shorthand way of saying 12, right? A mole is just a shorthand way of saying 6 times 10 to the 23rd of something. It's an odd number, also known as Avogadro's number. Not avocado. Avogadro is one of the founders of modern chemistry. I think his name was Enrico Avogadro, the Italian guy from around the, I want to say the early 1400s. And he came up with this way of describing it. Initially, he said this is the number of atoms in 1 gram of hydrogen, was his initial definition. And because they had grams at that point, and he said, well, I need a way to count how many objects I have. Grams is convenient and it's here, so I'm just going to say a gram of hydrogen is this many hydrogen atoms. And he worked the math backwards and was able to come up with a measured number for how many atoms that was. Is this exact?
No.
Could we actually have, if we actually went out 23 decimal places and were capable of measuring individual atoms with no uncertainty, then it would be a counting number, and but it's a little bit like measuring attendance at a baseball game.
It can't be because he worked the math backwards, so that is just a...
Right, he wasn't measuring individual atoms, so he was measuring backwards from the masses of these atoms. So it is a measured number, and attendance at a baseball game is a good analogy. It's supposed to be a counting number, right? Ideally, you would be able to say, well, it's exactly this many people, no more, no less at a baseball game. But if you have 23,000 people in a stadium, is it actually going to be the exact number you counted, or did you probably miss something somewhere? Is there some uncertainty there?
Yeah, people are sneaking in.
People are sneaking in. Maybe you miscounted somewhere between 22,292 and 22,294. You missed something. Easy to do, right? So it's not an exact number, it's a measured number. But all it is a way of counting how many objects we have. We don't really use it for anything but atoms and molecules. Because very, very quickly, this is a huge number, right? 10 to the 6th is a million. So 10 to the 9 is a billion. So 10 to the 12 is a trillion. If this was 10 to the 24, it'd be a trillion trillion.
Nice.
Right, so that's a huge number of anything. If you had a mole of ping pong balls, it would be enough to cover the entire surface of the Earth in a layer about a mile thick.
That's a lot of ping pong balls.
It's a lot of ping pong balls. It's also a decent estimate for the number of grains of sand on the planet Earth. Wow. So really, really big number. Also, just as another good point of reference, this number in kilograms is roughly the size, very roughly, but it's roughly the size of the moon. So it's a huge number. We really only use it for individual or for counting molecules and atoms because they're so tiny. The fact that we have this definition of atomic mass units, so Avogadro was doing this, he kind of was pioneering what an atom was, right? This is right around when Dalton came up with his atomic theory. So he didn't, it was kind of the Wild West at that point. He's like, well, I'm just going to say this is true, and that's going to make things easier for us. And what it also does, though, is it turns the mass number on the periodic table into grams per mole. The fact that he defined this 1 gram equals this many AMU means that the mass number on the periodic table is in more useful units. Technically, it's in AMU, and it's the mass of an individual atom. But realistically, the way we're going to use it is all of these mass units are in grams per mole.
So AMU equals grams per mole then?
AMU equals grams per mole. AMU is the mass per atom. Grams per mole is the mass per mole.
Okay.
there is a conversion for AMU to kilograms. It's like 1.7 times 10 to the minus 26 kilograms is 1 AMU. It's a stupidly small number. So we're going to stick with mostly grams per mole because we don't care about individual atoms. We care about groups of atoms, and this is our most convenient way of defining a group, is a mole. So if we had 3.42 moles of iron atoms, how many grams would that be? Conversion, exactly. It's a combined unit, right? Just like density. 1 mole equals this many grams. So if you have moles and you want grams, make moles cancel out.
And some change? But what do you keep? Is it still the sig fig rule in this thing?
Still sig fig rules. So we started with 3 sig figs.
So
This is a measured number.
Oh, that's an exact number.
It's measured
That's different.
because it's an average of all these things, right?
Okay.
So that's why we usually have a lot more sig figs than you're going to need on your periodic table, so that this doesn't limit how many sig figs you get to keep. Because if I picked something where the mass on your periodic table only had like 2 sig figs, then that's going to limit how many sig figs we can keep a lot of the time.
So 191?
191 grams. Right, so it becomes important to pay attention to moles of what, because the same reason that if I said, okay, you have 3 cars, how much do they weigh? Well, what are the cars, right? If you don't know what the cars are, you don't know how much 3 of them weighs. If you have a mole of atoms, but you don't know what that atom is, you can't do this because you don't know what that conversion is. But it also means your periodic table is another conversion sheet. Anything that's made up of matter, which is, everything, is on this conversion sheet. If you want to know how many objects you have, you just need to know the mass and what it is.
I'm sorry.
How many protons are in 10 grams of iron?
So if it's 26 are in 1, is that how you look at it?
There's 26 protons in 1 iron, which means there's 26 moles of protons in a mole of iron. Right? Because the same way that if I said that there's, if you have every car has 4 wheels, I could say a dozen cars has 4 dozen wheels. So if you say every iron atom has 26 protons, you could also say a mole of iron atoms has 26 moles of protons. But you're adding the same counting number on both sides of your conversion.
Yeah.
So if we have 10 grams and we want to know how many protons there are, we're just going to go from grams to moles of iron to moles of protons. Now we want grams of iron to cancel out, so we're going to use our atomic mass still, but we're going to put the grams on bottom. That'll give me moles of iron. And then, and just to ran myself out of space here, we're going to get what for moles of iron? 0.179. Thank you. Now, if we want to get this to moles of protons, we use the periodic table to come up with another conversion. That conversion is 1 mole of Fe equals 26 moles of protons. Because the atomic number is 26, that tells us every iron atom has 26 protons. So if that's our conversion now,
26.
we want cancel out moles of iron, so 1 mole of iron goes on bottom. And we get something about 5? No.
Something like, yeah, 4.65.
Right, so there's a reason why we spend so much time on conversions and how to turn percentages into conversions and speeds into conversions and everything else into conversions. It's because your periodic table is also a bunch of conversions.
It's asking how many protons, not how many moles of protons.
So if we want to know how many protons, generally, so this is a number of protons. The way that I would read this question, normally I would stop here. But if we wanted to get an actual number, we just go one spot further.
Multiplied by all that.
Yeah, we can say 1 mole of anything. In this case, 1 mole of protons is 6.022 times 10 to the 23rd of that object. Right, 1 mole goes on bottom. 6.022 times 10 to the 23rd goes on top. And we'll get a really, really big number in times 10 to the 24th. So we'll get something like 28. 2.8 times 10 to the 24th.
Yeah, I got 2.8. I didn't get 4.65 though. But I got the same answer at the end.
That's interesting. I'd have to look at exactly what you plugged in. You probably made what are called offsetting errors, where you made a mistake getting here and then you unmade the mistake by making the mistake again, going to the next step.
Oh, maybe.
So 2.8.
By 10 to the 24th.
2.8 what? You can keep 3 sig figs.
0.
There we go. Times 10 to the 24th, thank you. That's
P plus.
protons. Right, generally speaking, this is a more friendly number to work with. So having a mole of something, once we're comfortable with the fact that a mole is just a group of things, we can just leave it here. The same way as, if I walk in with 10 boxes of donuts and each box has 10 donuts or 12 donuts in it, let's not go with the baker's dozen. Let's assume every box has 12 donuts in it. I can just say I have 10 dozen, right? I don't need to do the math to say that's 120 donuts. This is like saying 10 dozen. Easier than saying 120 or 2.8 times 10 to the 24. All right, so with all that said, I believe that's everything. We definitely got through everything you need to do the ICA for this week. It'll still make you think outside the box a little bit and use some of this with some of the other stuff we've talked about.
Can we go over natural abundance a little bit?
Yes, I think that's a good idea. So if we have, natural abundance is basically the percentages that give us this weighted average. So mathematically, it's going to look very similar to what we did with the grades in Excel at the beginning of the quarter, where we said, okay, I'm going to take my score in homework times 0.5, and I'm going to take my score in quizzes times 0.3, and then I'm going to take my score on the exam and times 0.2 and add it all together to get a weighted average for the total grade. This is like the total grade, except that the weights are how common the individual isotopes are. Right, so for instance, for chlorine, the one that I did, since I happen to know those ones off the top of my head, or at least close to, we can say that, okay, well, chlorine has 2 isotopes, 37 and chlorine 35. If I want to know what the atomic mass is of chlorine, I need to average these two, and I need the percent abundances to do it. So the percent abundance is just what is the ratio, the percentage of the atoms that are normally that specific isotope. Right, so in a lot of times when it's written as a fraction, as a decimal, we call it the mole fraction. And we use this sort of script X, it's actually Greek letter chi, to say, okay, the percent abundance of chlorine 35 is, 74.2%. Actually, if it's a fraction, we usually would write it as the decimal, not the percentage. So 742 is our percent abundance. This is our fraction of those atoms we're going to have. So the fraction is always going to be between 1 and 0. The same way that a percentage is between 0 and 100. So if we want to know what the molecular weight of chlorine is, we just need to know what the mass of the individual isotopes are and what the percent abundances are. We take the percent abundance, or as a fraction, the fractional abundance, and multiply it by each of the individual scores, which is the weight of those isotopes. Right, so mathematically, the way we would write it is that your atomic mass is equal to the sum for all of your percent or your fractional abundances times the mass of that isotope. So take all of the individual members, this just means sum. For all isotopes that are naturally occurring, you just need the percent abundance and the mass. And you just multiply those and add everything up. So for chlorine, let's assume we're just going to call the mass of these 37 and 35, since it's pretty close. The atomic mass, we could write it mathematically as the percent abundance of 35 times the mass of 35, plus the percent abundance of 37 times the mass of 37. Now we've got an algebra expression, right? If I'm not asking you to solve for a percent abundance, if I just want to know what the weighted average is, you just need these pieces over here, right? And then it's plug and chug. If you need to solve for a percent abundance, still works. I still have to give you, all but one of the pieces, or you have to write some more algebra equations.
I see.
So if we call the mass of 35, just call it 35, since within sig figs it's going to be pretty close. Considering I just made that number up off the top of my head and guessed that's where our uncertainty is anyway. So our atomic mass would just be 0.742 times 35 AMU, or grams per mole. You could write either way. What's our percent abundance of chlorine 37?
1, 2, 6, 8,
And how'd you get there, Adam?
27.2.
All of your fractional abundances have to add up to 1. All of your naturally occurring isotopes have to add up to a probability of 1. Right, so in this case, there's only 2 naturally occurring isotopes, so we can say the fractional abundance of 35 plus the fractional abundance of 37 equals 1. If there were more isotopes, we just have more terms here. This is just like saying for a copper and lead problem, where we said, okay, well, the mass of copper plus the mass of lead has to equal the total, right? In this case, the total always has to be 1, because we're talking about a probability, basically. So that means that our percent abundance of 37 is just 1 minus 0.742. 0.2, I went the wrong way. Dang it, I might have even gotten the right number, but I went the wrong way with it. So we're gonna get a number that's higher than the real atomic mass. Right, so that's all your percent abundance is when it's a percent. When we turn that into a decimal, I don't know why they feel the need to confuse fractions and decimals, but they call it the fractional abundance, even though it's as a decimal, not a fraction. And this is how we use it. Your abundance times the mass of that isotope. You just add everything up. And it should add up to something that matches relatively closely the periodic table. What do we get for an answer here? Just out of curiosity. I'm going to guess 35.55. 35.5 something. I'll just keep guessing digits until you guys correct me. We need more sig figs. We should actually only be keeping 3 sig figs at most anyway. 0.886. And that's why when you look at the homeworks that deal with the percent abundance, there's a ton of sig figs on everything, because otherwise you wind up not being able to tell the difference, because you need a lot of sig figs in order to tell, to get past this 10th place, right? And since most of the atomic masses go to the thousandths, we need five or six sig figs on all of our percent abundances and masses as well. Rose?
It only gave me 5 6 35.8.
Oh, so I wasn't even that close. Oh, I was way up.
I was damn close. 0.3.
I knew what it should be on here, so I was trying to fudge the numbers and come up with the percent abundances off the top of my head that were going to give us this number. And for how well I knew that number, I should have been able to get close, but let's not worry about that. The process remains the same. If you have in specific enriched samples, enriched generally means they've been processed to have more than the normal natural abundance of a specific isotope. So enriched uranium means that they've taken the uranium that's naturally occurring and they've made it so that they have more than normal abundance of uranium-238 or 235 generally. By basically, generally they actually just put it in a super big centrifuge that generates like hundreds of thousands of G's of gravity. And they just use this solid material, they just use gravity with these giant centrifuges to separate the heaviest isotopes, so they're going to be the ones that settle to the bottom. And incidentally, that's one of the ways that they can tell whether certain countries are trying to enrich uranium for power plants versus bombs, is the size of the centrifuge you need to enrich uranium to get it to weapons grade is off the charts compared to what you need to make it power plant grade. So it's really, really obvious to UN inspectors when they're building an enrichment facility that's supposed to enrich to weapons grade versus power plant grade. Which is why places like North Korea just don't let the inspectors in, because then they can't tell them that you're doing it wrong or that they're making weapons. It's basically like pleading the fifth in the international court. If you won't allow the UN's weapons inspectors to inspect your enrichment facility, you're basically saying we're making weapons grade uranium without officially saying it.
If you don't have anything to hide, you just don't really need to hide anything.
Generally speaking, yeah, they don't. Countries that aren't trying to make nuclear weapons are not fighting.
Pretty cynical view of the Fifth Amendment.
It's when the Fifth Amendment is used poorly. The Fifth Amendment can be used in a way that does not just mean I'm clearly guilty, therefore I don't want to say anything, but the way it's most commonly used, at least in popular society, is, I plead the fifth, right? If your significant other asks you if they look fat in this outfit and you say, I plead the fifth, you're not really helping your case, right?
Just lie.
The best option is to say something that is true that dodges the question. Oh, you look beautiful.
Asking why by omission.
No, you redirect.
Redirect.
That's a nice way of saying it.
All right. Again, fairly cynical view of things, but
You just went past these questions then?
I did.
Okay.
So these are more practice with percent by mass. If we have an ore deposit that is 100 kilograms, how many moles of iron do we have? We have everything we need here to do this. Because if we have iron ore that has this percent by mass, it's usually iron oxide. Usually you mine the iron as rust, basically. And then you take the iron oxide and turn it back to metallic iron by feeding it with carbon monoxide in really, really high temperatures. And you can get the carbon monoxide to oxidize to make CO2, and that reduces the iron oxide back to metallic iron. So we don't actually mine most metals as their metallic form. Basically just copper, silver, and gold are the only ones we see in nature as metals.
Pure forms at least.
No, I think, mercury.
Oh, yeah.
We do find mercury mixed in with silver. If you process it, you can separate them. If we want to answer this question, we have 100 kilograms of iron, and we want to know how many moles of iron metal that is. Should be looking familiar, right? It's going the opposite direction. Instead of trying to figure out how much ore you need, we're starting from the amount of ore to figure out how much metal there is. But yeah, we have a percentage, so we could actually switch it from, we could switch from kilograms to grams first. 1 kilogram is 10 to the 3 grams. And then we can say for every 100 grams of ore, because we're in grams of ore right now, 100 grams of ore is 69.9 grams of iron.
Well, real quick, because it's 69%, isn't it 0.699?
So if we put 100 on the bottom,
Oh,
we leave it as,
gotcha.
if we put this as 1, we would say 0.699. And then last but not least, we're in grams of iron now. We want moles of iron. We use anytime you want to get to moles of something from a mass, you use the atomic mass. So for every 55.845 grams is 1 mole of iron. So we're going to get 100,000, 60,000, 70,000 divided by 55. We'll get something like, 100 moles?
1,000 moles.
1,000 moles. Slip the digit.
1260.
1260.
Yeah. Is that right?
I have 12 and 6, that's because I put the right math, 6.
So to make it non-ambiguous, 1.26 times 10. Oh, we had 4 sig figs at the beginning.
Yeah.
No, we only have 3 sig figs there.
Oh, well, I did it differently.
If you used this percentage, though, this is a measured percentage, which means this is controlling how many sig figs on our answer. So 1.26 times 10 to the 3rd moles.
I see you.
A note about abbreviating moles. It only saves us 1 letter to abbreviate moles to MOL. But you can't abbreviate it further because there are too many units that have M involved, right? So to avoid any confusion and avoid confusing it with molybdenum, which is MO, just write MOL. And if you actually mean molecules, if you mean individual atoms or molecules, don't abbreviate that at all. Write out molecules or atoms so that we know we're not talking about moles of something. So if we went all the way to how many atoms of iron, we would have to write, we wouldn't just write this many iron. We'd write atoms of iron. Let's see. Some more practice with weighted averages and atomic mass. We'll do the qualitative answer here. Carbon has two naturally occurring isotopes, carbon-13 and carbon-12. Carbon-14 is not considered naturally occurring because it only happens when high-energy photons hit the upper atmosphere. So it is the amount that is on the ground is 0. The amount that's incorporated into living things is not 0. But so we would say that carbon has two naturally occurring isotopes. We would leave out carbon-14 because that requires sunlight to form. That's all beside the point. If we know we have carbon-13 and carbon-12, and the mass of carbon on the periodic table is
12.011.
That's probably really hard to see.
That's good.
Which of those isotopes is more common?
12.
12, by a fair bit, right? We're really close to a mass of 12. In what ratio? We could do it mathematically. We could solve for these. We set it up 12.011 equals abundance of carbon-12 times 12 plus the abundance of carbon-13 times 13 for the mass of carbon-13. And then we could say, well, now we still have two unknowns though, right? What else could we say to solve this? We need another algebra equation that involves these fractions.
Hi, why can't you just look at that number and say it was 99% carbon-12 and they wanted to hit 113?
And how do you know that?
Because 0.01.
Yeah.
There's 99%.
It's gonna be, you're right.
Show your work.
I'm not saying you're wrong.
Show your work.
But we gotta know why that's,
Show your work.
how do you know that it's not 50% carbon-12 and 10% carbon-13? Because what? No? Mathematically, we know that they have to add up to 1. In other words, the percentages have to add up to 100. That's how you can say that intuitively that it's going to be about 1% of its carbon-13 and most of its carbon-12. Because you know that there's only two pieces and that together those probabilities have to add up to 1. Right, the same way that over here we did it, we said, okay, well, we know the fractional abundance of carbon-37, or carbon-30, chlorine-35. And from that, we could work out the abundance of chlorine-37. This was the equation that let us do it. The pieces of the abundances have to add up to 1. The percentages on your grades have to add up to 100%, right? If I say that the class is 50% quizzes and 10% tests, and then I stop, what's your first response? What about the other 40%, right? So that's intuitively doing what we're showing mathematically here. So in other words, we can turn around and say 12.011 equals mole fraction of 12 times 12 plus 1 minus the mole fraction of 12 times 13. I just solved this for mole fraction of 13 and plugged it in. I did substitution just like we did last week. Now we have a way to mathematically say it. In case it's not entirely obvious, just by looking at it, it's about 1%. And we would, in fact, solve this mole fraction of 12. When we solve this, will come out to be 0.99, 0.989. All right. We're over time. We did not. We'll start with Mendeleev. It's actually a perfect place to stop. We'll start with that fun-looking guy on Tuesday.
Dumbledore.
Wow.
The first one, though, not
That's enough chemistry for one day.
There's two actors down.
They're not coming anymore. They come to mind.
No problem. Have a good one. I'm glad you enjoyed it.
Encore.
So if you're curious about the synthetic elements, and this is what's called the island of stability. So this is a graph of the neutrons versus protons in isotopes, and the color is their half-life. So things that are black have a half-life that's greater than a year. And you'll notice there are a couple in the synthetic region that have a half-life greater than a year, a couple different isotopes. There's also this section over here that we predict should be stable, relatively stable. We haven't made any of those yet, and there could be some that are even more stable than we predicted there, because things get a little bit funky when you try to extrapolate what we know into unknown areas, right? That's why they're working really hard to try and find these ones to see maybe they might be really stable. At the very least, it'll be really interesting.
Yeah. That's cool.
It is. It's called the island of stability. If you look up the island of stability, you get a whole article about this. Not a speech by Jimmy Carter. Apparently that was a thing in the 80s.
Not Wikipedia.
Oh, another thing recently.
Hmm.
Do you know who helped bring sci-fi to a much wider